Imagine, beyond the edge of our solar system, there might be a huge structure that surrounds our sun and all the planets, but we've never actually seen it. It's like a shell made of billions, or even trillions of mountain-sized ancient ice bodies. That's the boundary of our solar system. This region, known as the Oort Cloud, is unimaginably distant from us. Even our most powerful telescopes can hardly glimpse its true appearance. It is shrouded in mystery and speculation. Located where the sun's gravity gradually weakens and begins to touch the void of interstellar space. So, what exactly is the Oort Cloud? If we've never directly observed it, how do we know it exists? And why do some people question it? Today, let's explore together this unsolved mystery at the edge of the solar system. To understand the Oort Cloud, let's first get familiar with the solar system. You may know, is made up of millions of rocky asteroids. Further out, beyond Neptune's orbit, is the Kuiper Belt. In the mid-20th century, astronomer Oort Cloud proposed that this is the cradle of short-period comets. The Kuiper Belt is a vast region of icy debris. Occasionally, some of these fragments are gravitationally disturbed and pushed into a new orbit closer to the Sun. Sometimes it forms a new short-period comet. These comets typically have orbital periods of less than 200 years, and their return is relatively predictable. Just as Kuiper was studying short-period comets, another distinguished astronomer, Jan Oort from the Netherlands, began to think about the origin of long-period comets. Oort was a leading figure in 20th century astronomy, with remarkable contributions. For example, he calculated dark matter in the and first discovered clues to the existence of dark matter. In 1950, Oort proposed a revolutionary theory. At the distant edge of the solar system, there exists a massive, roughly spherical cloud of icy debris. This is what we call the Oort Cloud today. He believed this is where those long-period comets come from. However, unlike the asteroid belt and Kuiper Belt, the Oort Cloud has not been directly observed to this day. Oort's theory, based on in-depth observations of long-period comets. These comets are very different from short-period ones. Their orbital periods are surprisingly long. Some even take tens of millions of years to orbit the Sun once. And their whereabouts are erratic from all directions of the universe. The orbital inclinations are also different. This is a grand puzzle. But Oort discovered key clues. First, the orbits of these comets show they do not come from the distant depths of interstellar space. Their source should be closer to the solar system. Secondly, he noticed an amazing pattern. All observed long-period comets, the point on their orbit farthest from the Sun, that is, the aphelion, are clustered at a distance of about 7.5 trillion kilometers from the Sun. That's right. It is 7.5 trillion kilometers. In the face of such a distant distance, it is really inconvenient to measure in kilometers. Astronomers usually use astronomical units AU. 1 AU is the average distance from the Earth to the Sun, approximately equal to 150 million kilometers. The aphelion cluster discovered by Oort, about 50,000 Australian dollars. Other key distances are also marked on the screen. As a reference, Neptune is about 30 Australian dollars. The main body of the Kuiper Belt is between 30 to 50 AU. Its outer scattering disk may extend to about 1,000 AU. The inner edge of the Oort Cloud, then at a more distant about 2,000 AU. Combining these key findings, long-period comets do not come from the depths of interstellar space. or Kuiper Belt. Their aphelions are concentrated at about 50,000 Australian dollars. Oort deduced. On the outskirts of the solar system, there must be a huge, spherically distributed cloud of icy debris. This is the source library for long-period comets. So, how did the Oort cloud form? The mainstream theory believes that it originated about 4.6 billion years ago, residual material from the birth of the solar system. After the planets formed, there are also a large number of icy rock fragments called planetesimals scattered around. The powerful gravity of the early giant planets acted like a slingshot. These planetesimals, violently thrown to all directions of the solar system. Some were completely thrown out of the solar system. But there are still a huge number of planetesimals, was thrown into extremely distant, highly elliptical, randomly oriented orbits. Although these orbits are subject to the gravity of the Milky Way, or the influence of passing stars, but they are still bound by the sun's gravity. In this way, billions or even trillions of icy celestial bodies constitutes the Oort cloud we speculate today. Gravitational perturbation also explains how comets are produced. Just like Kuiper Belt objects are disturbed, will form short-period comets. When the celestial bodies in the Oort cloud, when subjected to external gravitational interference, they may be kicked into the inner solar system, enter a long elliptical orbit, thus becoming a long-period comet. And this interference may come from passing stars, huge molecular clouds, even the tidal force of the Milky Way itself. About 70,000 years ago, there was such a close encounter. A binary star system called the Shoals star became the closest known star to the solar system. It even passed the outer reaches of the Oort cloud. Fortunately, because its mass is much smaller than the Sun, this encounter did not cause disastrous consequences. However, a 2018 simulation study showed that Shoals's magnetic gravity did disturb some Oort cloud objects. Influence even shaped the trajectories of some long-period comets. The Sun has existed for 4.6 billion years. Close encounters with stars like this may have happened many times in the past. But models show that this does not prevent the formation of the Oort cloud. Instead, it may allow the Oort cloud to exchange matter with similar clouds of other stars. In fact, the latest simulation studies also support the possibility that other stars have their own Oort clouds. Regarding the structure of the Oort cloud, scientists speculate that it may be divided into inner and outer layers. The inner region may be shaped more like a posterior disk, similar to an enlarged Kuiper belt, while the outer region constitutes the well-known huge spherical shell. The entire inner edge of the Oort cloud is about 2,000 Australian dollars from the Sun. Its outer edge extends deep into interstellar space, possibly as far as 100,000 Australian dollars or more. This means that to understand how far this is, let's look at the journey of Voyager 2. Since its launch from Earth in August 1977 until the making of this video, Voyager 2 has traveled approximately 139 Australian dollars. Its speed is approximately 3 Australian dollars and 30 cents per year, or 56,000 kilometers per hour. It is launched by humans. The second farthest probe from Earth, August 2007. It crossed the heliopause. The heliopause extends far beyond the orbit of the planets, is 3 times the distance of Pluto. Outside the heliopause, the stream of charged particles from Sun, solar wind, is finally blocked by the interstellar medium. November 2018. Voyager 2 successfully crossed the solar wind, the fine arena and direction of the interstellar medium. The heliosheath officially entered interstellar space. However, far beyond the Kuiper belt, it will need to fly for about another 300 years to reach the theoretical inner edge of the Oort cloud. And to completely traverse the entire Oort Cloud, that could take another 30,000 years. Imagine flying at a speed of 56,000 kilometers per hour to cross a distance of only 1.5 light years. It takes so long. This illustrates the huge challenges facing interstellar travel. You know, Proxima Centauri, the nearest star to us, also 4.25 light years away. Nevertheless, some people question the existence of the Oort Cloud. The main reason is, we have never seen it directly. Some also suggested long-period comets may come from interstellar space. In fact, in 2019, amateur astronomer Gennady Borisov discovered a interstellar comet from outside the solar system, named Borisov. Follow-up studies have shown its ingredients, especially the content of carbon monoxide, significantly different from comets in our solar system, suggesting it may have formed near a red dwarf star. However, the vast majority of astronomers still firmly believe that the Oort Cloud really exists. A lot of indirect evidence and mathematical models all strongly support this theory. Interstellar comets are just rare exceptions, cannot explain the large number and orbital characteristics, such as aphelion aggregation, highly consistent long-period comet group. Then, why can't we see the Oort Cloud? The key lies in distance and light. Imagine an Oort Cloud fragment, about the size of Mount Everest on Earth, about 9 kilometers high. How far is it from the Sun? The nearest one may be more than 2,000 Australian dollars away, about 45 billion kilometers. The distance from the Sun to this fragment, tens of millions of times the size of the fragment itself. This is countless times more difficult than finding a needle in a haystack. More importantly, stars and galaxies emit their own light, and planets or asteroid belts, Kuiper belt objects. Because it's closer to the Sun, it can reflect enough sunlight for us to see. But Oort Cloud fragments are extremely far from the Sun. The sunlight received is extremely weak. The light reflected back to Earth is even more negligible, completely submerged in the dark background. No matter how powerful our telescopes are, currently unable to capture. This is from the most remote frontier of the solar system. Extremely faint echo. Therefore, although the Oort Cloud in theory, described as large-scale, and is crucial to understanding long-period comets, we can only use sophisticated mathematical models at present, and solid indirect evidence, to infer its existence. This can't help but remind people of a glorious moment in the history of science. Copernicus and Galileo in the 17th century, when they proposed the heliocentric theory that the Earth revolves around the Sun, not based on direct space observations, but through precise calculations of planetary motion and reasoning. Later facts proved their theory is correct. This is the charm of scientific exploration. Constantly asking questions, looking for evidence, constructing theories, and be brave enough to accept future tests. Maybe 100 years later, new technology will eventually reveal the mysteries of the Oort Cloud. Perhaps scientists will discover a brand new explanation for the origin of long-period comets. But no matter the outcome, the process of pursuing answers itself, pushing humanity's understanding of the universe, continues to expand. And the Oort Cloud, as the frontier of the solar system, one of the most fascinating mysteries, will continue to inspire us to explore the vast starry sky. Infinite curiosity and imagination.